So my group is focused on understanding what it is about the climate system that most impacts us. And that means that we're addressing a series of questions that are right at the interface of climate dynamics and climate impacts. And one question that has been emerging increasingly, both within the scientific community and beyond the scientific community, is how much climate change are we likely to face, and how soon? And there's a couple ways that this question's been approached. One is to use some statistical method to extrapolate the historical global temperature time series. And the good news is those are real observations. The challenge is that it's ambiguous. Right? What is internal climate variability, and what's the response to climate forcing? An alternative is to leverage this really foundational relationship between the total cumulative greenhouse gas emissions and the amount of global warming. And colleagues here at Stanford and elsewhere have used this to create carbon budgets for the total amount of emissions for different global warming levels. And this has been really powerful and really influential. It also relies on global climate models. And one of the challenges of global climate models is, even though they are very comprehensive, very sophisticated, there is quite a bit of uncertainty. They do have limits. And if we look at something like how many years until we'll reach 1.5 degrees, you can see on the bottom right that the spread is very large, a couple decades, including should have already happened more than a decade ago or might not happen for another decade in the future. So one of the questions that I've been working on with my colleague Libby Barnes, who's a professor at Colorado State, is whether we can use artificial neural networks to build a bridge between the vast archives of global climate model simulations that do give us a representation of the physical mechanisms that govern Earth's climate, and then bridge to the real observations of the real world. And the basic approach that we use is we train the neural networks entirely on the global climate models. Right? So this is, for the results that I show from here on out, it's really important to keep this in mind, that the machine learning is entirely on the global climate models. And then once we've trained, tested, and validated, we freeze the networks. And then we use the actual real-world observations as truly out-of-sample inputs to make a prediction. So the first question we've approached using this framework is how long until some specific level of global warming is likely to be reached in a given greenhouse gas emission scenario. And here we're using the map of global temperature anomalies as the input. And you can see here an illustration of what I said earlier, which is that the historical observations reflect not only the forced response to the climate forcing, but also the internal variability. And what we're asking the network, training the network to learn, is what are the most reliable indicators of, in this case, how many years until some global temperature threshold is going to be reached. And we're trying to do this as true predictions. So the first question we ask is, can we set up a setting where we can use what happened historically to test this as a prediction? And so what you see here on the left side, the left of those two subpanels, is the time series of predicted time until the global warming at the end of the 2020s was reached. And this is as a future prediction. We're using the 1.1 degree threshold here in 2020, 2021, because that's the IPCC assessment in the AR6 of the historical global warming. What I want you to focus on here is the one you see the median prediction as well as the uncertainty. And then as we come over the last couple decades here, you can see this very systematic march of about 1 degree per year in the predicted time until the historical warming level is reached. And what this means is that the network has, in fact, learned what to ignore in all of this spatial noise and instead is finding the indicators for the time until the global warming's reached. So that gave us confidence. At the end of this time series here, then you can see the PDF on the right. So this is in 2021, given that map, how many years until 1.1 degrees C is reached, and you can see it's 1 more year plus or minus 5 years. Right? So spot on prediction, having never seen the real observations. So that led us to feel confident in using this framework to predict the future. On the bottom left, you see the results for the 1.5 degree threshold, and this is quite in line with what other assessments had made. Okay, so likely early 2030s and very little difference between different greenhouse gas scenarios, whether high, intermediate, or low emission scenarios. In contrast, on the right, for the 2 degree threshold, what we found is that the network predicted, if you focus on the light blue, this is a low emission scenario that reaches net zero in the 2070s. And you'll see a very high likelihood of reaching the 2 degree warming level in this scenario. And this was much earlier, much higher level of warming, much earlier arrival at 2 degrees C in a decarbonization scenario than the IPCC and other assessments had predicted. So this got us focused on this question of how hot could conditions get if the world achieves our very ambitious decarbonization goals. So in this case, we have a challenge in that we don't know what the future decarbonization rate will be. So we have 3 scenarios here from the IPCC of different rates of decarbonization. There's obviously a lot of human factors that will determine what that rate is. However, if you look along any of these 3 decarbonization scenarios, you can see quite a range in the amount of global warming that the GCMs project will be reached. So we want to, again, use the neural networks to make a prediction. We train across all 3 of these scenarios, and then again use the actual historical observations to make a prediction. And in this case, a key addition that we've made is to let the networks know what the amount of total future cumulative emissions is. Okay, so in any given year, the network knows the map of the global temperature anomalies, and it knows what's the total mass of CO2 emissions left. And again, we first want to test this prediction framework using the historical record. So here we're asking if we ran this back when I was in high school and college, it's middle and high school and college, what would the prediction have been? So for the last 2 decades of the 20th century, you can see in each year, using now the real observations as the inputs, you can see the median prediction and the uncertainty. And then we asked, okay, if we just stop that, we take the average prediction, what's the hottest individual year that's likely to occur by 2023? And in fact, when we look at the real temperature observations, again, the network's highly accurate. Again, never having seen the observations in the training, testing, or validation, truly out of sample prediction. So again, we felt confident in using this to predict future global warming. And in this case, you're seeing a familiar format of this plot. On the horizontal axis is the total remaining cumulative emissions from 2024 onwards. So this is future range of emissions. And then on the vertical axis is the mean long-term warming. Right? So how much long-term global warming are we likely to experience for different levels of cumulative emissions? And here the colors are showing the uncertainty. You can see the expected proportional relationship, and you can also see that the uncertainty increases as we get to higher levels of emissions, particularly at the hot tail. So we're just going to take a cross-section across each of these 3 IPCC scenarios and look at the uncertainty. So if you focus first on the light blue, this is a very rapid decarbonization, reaching net zero in the mid-2050s and exhibiting very deep negative emissions after that. If you look on the right at that PDF, you'll see that it is virtually certain, according to this prediction, that global warming will exceed 1.5 degrees. And there's about even odds of reaching 2 degrees. Okay, so again, this has been considered a realistic 1.5 compliance scenario. This framework says no, and in fact, it's a coin toss about exceeding 2 degrees. On the other hand, if the world takes a more gradual emissions trajectory and something like the orange trajectory, where decarbonization does occur but doesn't reach net zero by the end of the century, you can see around a 90% chance of having at least 3 degrees of global warming with substantial probabilities of much higher levels of warming. So that's for the mean global warming. We're also interested in the hottest year, particularly given how hot recent years have been and how severe the impacts that we've experienced around the world. So this is the same framework, but instead predicting the hottest year by the end of the 21st century. Again, if you look at the light blue PDF, 90% chance of the hottest year being at least half a degree hotter than what we experienced in 2023 and 2024. You look at the orange, now 90% chance of the hottest year being at least twice as large in terms of the departure from the pre-industrial, 3 degrees as opposed to 1.5, which we've experienced in the last couple of years. So what this suggests is that even if decarbonization is successful, we are very likely to experience higher levels of warming than other methods suggest, and the potential for very hot individual years. So that increases our interest in what might the individual local and regional extreme events be if we have global years that are this hot even under decarbonization. So again, we've used machine learning, and in this case, we're again training on the global climate model simulations, but we're training on each day the weather maps, the kind of weather maps you're used to seeing on the evening news or on your phone in terms of the atmospheric conditions, the land surface conditions on each day. And then we also have a variable that is the global mean temperature anomaly, right? So how hot was the global mean temperature in the last 12 months? And what this allows us to do is, once we've trained, tested, and validated the network, is we can use the actual weather patterns from the historical time period, right? What we know actually was produced by Earth in any given region historically. And we can take those exact weather patterns and ask if the global mean temperature anomaly were different, right? If it were a hotter or cooler year, what would the regional local conditions be? So we've looked first at this heat wave that occurred over North America in the summer of 2023. And this was a record-setting heat event. And as you can see, the neural network very accurately predicts, again, out of sample, in this case, the maximum daily temperatures over this region during this heat wave. So again, that gives us confidence in using this framework to ask how, if we get exactly the same weather conditions as have occurred historically, but at different global mean temperature anomalies, how often might we break this record? And on the bottom right, you can see there is some uncertainty, but once we get out to something like 2.25 or 2.5 degrees, what was the hottest event on record becomes an annual event in this region. We see similar results for other events in other regions, including events that have had very high impact when they occurred. The European heat wave in 2003 was a canonical event thought to have been essentially impossible at the time that occurred. And yet, again, if we get years that are around 2 degrees hotter than the pre-industrial, just a half a degree hotter than we've had this year, 50% chance of occurring in decarbonization that reaches net zero in the 2050s, that's an annual event. Okay, so this is raising the possibility of accelerating impacts. And there are a couple of reasons that we can expect impacts to accelerate even if decarbonization is successful. One is the well-understood simple statistics of the Gaussian distribution for a variable like temperature that's pretty Gaussian in most parts of the world, right? A mean warming is going to give us an accelerating increase in the frequency of extremes just because of the shape of the distribution. However, there's a second reason that we should expect accelerating impacts. And that's because many natural and human systems, many sectors we now know, due to research here at Stanford and elsewhere, including by people who are now at Stanford, it's clear from empirical work that many natural and human systems experience accelerating impacts from extreme events. Right? So there's a double exponential here, both in the frequency of extreme events and in the sensitivity to extreme events. And what that means is that even if decarbonization is successful, we're going to need other solutions if we want to be able to successfully manage climate risks. It's going to require accelerating solutions also in adaptation and sustainable development. That's going to require not just working on solutions, it's going to require working really hard on understanding how the world works. And that's what makes me really excited to be part of this school. Thank you.